Hello everyone, this is Surajit and welcome to our channel. In last lecture, we have talked about electric field lines, their mathematical representation, and their key properties. And towards the end, we have also discussed the concept of electric flux and the flux density. So in this video, we'll dive deeper and we'll learn how to calculate flux for different cases. Now, when I said different cases, that's mean say in the last class we have defined this flux in this way, where let's say this is the surface, and if we place this surface in an electric field E, then in order to calculate this flux through this surface, what we have to do, first we have to take the dot product of the electric field with the elementary area on this surface, and then we have to take the surface centrical over this surface, and that will give us the total electric field. Now these calculations will be easy if we know the nature of electric field and the nature of surface through which we want to calculate the flux. Now when I said nature of electric fields, means either this electric fields can be uniform or it can be non-uniform, and also this area, that is the given surface can be open surface or it can be a closed surface. It can be open surface or it can be a closed surface. And also sometimes instead of electric field, examiner give us charge. So if we have a charge plus open surface or charge distribution plus closed surface, then also we'll learn how we can calculate the flux. And at the end we'll see if we place any closed surface in a non-uniform electric field, then how we can calculate the flux. So these are the different situations we'll talk about. We'll learn how to calculate flux for each situation. Okay, and also, so this is the plan of today's video. I will introduce each case one by one, and we'll solve at least 2-3 problems related to each cases. So in this way, you will get a clear idea how to calculate flux for different situations efficiently. So let's start with the first situation. So right here, case 1. Case 1. By case 1, let's say we have a uniform electric field. Uniform electric field. Uniform electric field plus a open surface. Okay, uniform electric field and a open surface. That's mean the given electric field is uniform and the surface through which you have to calculate the flux, it's an open surface. It's an open surface. Then how we can calculate the flux? How we can calculate the flux through this open surface? So let me just draw a simple diagram. Let's say this is an open surface. Let's say this is an open surface. Open surface means it doesn't enclose any volume. So it should be a plane surface like this. So it's plane surface. And if we place this plane surface in a uniform electric field means we can represent this uniform electric field by a set of parallel lines. And how we can check that given field is uniform or not? If we calculate the magnitude of the electric field, and if we see the directions of electric field, and if we found that everywhere the directions of electric field is same and the magnitude also same, then we can say this given electric field will be uniform electric field. And we can represent this uniform electric field by a set of parallel lines. So let's say these are the electric field lines. So this is the electric field. So in this case, say uniform electric field, so it means constant electric field. You can say any constant vector is uniform. Means the constants means the magnitude and directions both should be same everywhere. Everywhere magnitude would be same. At any point you calculate the any 2 point or any point you calculate the magnitude of this electric field, and if you see the direction should be same in a particular direction at every point, and magnitude will be same at every point. Then we can say it's a uniform electric field. So we have a uniform electric field and we have an open surface. So in this case, if we want to calculate the flux, then what we have to do? First, we have to take elementary area. So let's say this is the elementary area, ds. And then what we have to do in order to calculate the flux, we have to take the dot product of this electric field with this elementary area, and then we have to do the surface integral over the surface. But in this case, since it's a uniform electric field, that means on the surface at every point the magnitude of electric field will be same, and also the directions of electric field will also be same. Directions of electric field will be the same, or other way you can say the angle between electric field and the area vector will be same. So in this case, we can take this electric field out of the integration. Then what we'll get? We'll get E vector dot surface integral of elementary area. So when you do this integration, it will give you the total area of the given surface. Total area of the given surface. And if say total area of the given surface is A, then we can write simply dot product of electric field and the total area of the given surface. That will give the flux through this open surface. So if you have open surface plus a uniform electric field, then calculations of flux through this open surface will be super easy. We have to simply take the dot product and the total area vector of the given surface, and that will give us the flux, total flux. And sometimes also examiner asks flux density for this type of question. So what will be the flux density? Flux density means flux per unit area. This is the total flux through total area A. Now we have to calculate flux per unit area. That will be the flux density. So for that, what we have to do? We have to divide the total magnitude of area vector. We have to divide the flux by the magnitude of area vector. So when I do that, what we'll get? We'll get simply E vector dot A vector divided by magnitude of A vector, and that will give you the unit vector associated with the area vector. So if we want to calculate the flux density for this case where electric field is uniform and surface is open, so what we have to do is to simply take a dot product of unit vector associated with the area and electric field. And if we want to calculate total flux through this surface, then what you have to do? We have to take the dot product of area vector associated with the given surface and the given electric field. So let's solve some problem associated with this case. So this is the first question. So let's see, in this question is written, consider an electric field E is equals to E naught x cap. So this is the given electric field E naught x cap, where E naught is a constant. What we have to calculate? The flux through the shaded area as shown in the figure due to this field. Okay, so you have to calculate the flux through this surface. So you see, this is an open surface. It's a plain surface, means it will not enclose any volume. So it's open surface. So in this case, the given electric field is E naught x cap. So magnitude is E naught, and it is written that E naught is constant. And everywhere, doesn't matter if you put x is equals to 1, 2, 3 or 4, 5, 6. If you put any value of x, y, z, everywhere electric field will be always along the directions of positive x-axis. So in this case, electric field is also uniform. So we have a uniform electric field and we have an open surface, and now we have to calculate the flux through this open surface. So what we have to do, we have to take simply the dot product of given electric field and the total area of the given surface. Total area of the given surface. But in this question, total area of the given surface, total area of the surface is not given here. So what we have to do, first we have to calculate what will be the area of the given surface. Area of the given surface. So for that, you can see that the vertices of the surface is given here. Coordinate of the vertices is given here. Coordinate of this corner is 0, 0, 0. Coordinate of this corner is 0, A, 0. Coordinate of this corner is A, A, 0. And coordinate of this corner is A, 0, A. A, 0, A. So we can write the length of this side in terms of vector form. And also we can write length of this side of this surface in terms of in a vector form. In a vector form. And then if we take the cross product of these two sides, that will give the area of this surface, and then we have to take the dot product of this area with this electric field, and that will give us the total flux. Okay, so right here, so just right here, what will be the length vector of this side? So see, we have to write the position vector of this point with respect to origin. So in this case, coordinate of this point is 0, A, 0, and this coordinate of 0, 0, 0. This corner has position vector of coordinate is 0, 0, 0. So what we can write here, what will be the length vector of this side? It will be simply A, j cap. A, j cap. And same way we can also write the position vector of this corner with respect to this corner. So what will be this length? Again, in this case, it will be of A I cap plus 0 minus 0, so 0 j cap, and then A minus 0 k cap. So it will be A k cap. Okay, so these are the length vector of two sides of the given surface. So if we take the cross product of these two sides, that will give us the area of the given surface. So right here, the area of the given surface the area of the given surface, the area of the given surface is A vector is equals to A j cap cross A I cap plus A k cap, and this will give us simply, when you take the cross product of j cap with I cap, that will give you minus k cap. So it will be S square minus S square k cap, and I will take cross product of j cap with k cap, that will give you I cap. So it will be S square I cap. S square I cap. So this is the area vector of the given surface. So now we know the area vector, and we have also electric field. We have so electric field is equals to E naught x cap. Since we have written this area in terms of I cap, j cap, k cap, so we can write this x cap in terms of x cap, or we can write as I cap also. So let me write as an I cap. So this is the given electric field. Now we have also calculated the area of the given surface. So what will be then total flux? Therefore the flux through the surface through the given surface is phi is equals to, simply we have to take the dot product of electric field and the total area vector of the given surface. So electric field is E naught I cap dot, we have to take the area vector. Now we have to put the value of area vector. Area vector we can write S square I cap minus S square K cap. So when you take dot product, what you'll get? We'll get simply S square into E naught. S square into E naught. So that will be the total flux through this surface. Total flux through this surface. So what will be our answer then? So our answer will be 1. Is written E naught S square. So in this case, what will be our answer? Answer will be 1 into E naught S cap. So it will be 1. Okay. So this first example associated with first case, and then see this is the second example associated with first case. So in this questions, it is written an electric field E is equals to alpha, beta, alpha I cap, beta J cap, and gamma K cap exist in a space where alpha, beta, gamma are constant. The magnitude of electric flux per unit area through a plane surface AX cap, AX, BY, CZ equals to D. Okay. So in this case, what is written here that we have a electric field. You have an electric field E is equals to, you have electric field E is equals to alpha I cap, beta J cap plus gamma K cap. Gamma K cap. So in this case also you see where alpha, beta, gamma is constant. So in this case, if we calculate the magnitude, what will be the magnitude irrespective of any point? I mean, if you consider any value of x, y, z, everywhere the magnitude will be always under root of alpha square plus beta square plus gamma square. That's when magnitude is fixed. And also you see, it doesn't matter what value you are going to put x, y, z. If you put any value of x, y, z, everywhere this directions of the electric field will always remain same. So again, it's a uniform electric field. And then we have equations of this plane. Equations of this plane ax plus by plus cz equals to d. So again, it's a plane surface, so that's mean it will also be open surface. So in this case, what has been asked, what will be the total flux through this given surface per unit area? So that's mean we have to calculate the flux density through this plane. Flux density associated with the electric field through this plane. Through this plane. So what will be the flux density? We have already written here. If you want to calculate flux density to any surface, then what we have to do? We have to take simply, if it is a uniform electric field, then what do we have to do? We have to take simply this dot product of electric field and the area vector. Unit vector associated with the area vector of the given surface. So in this case also we have to calculate flux, and the conditions are satisfied. We have say electric field is uniform and the surface is open. So in order to calculate flux, what we have to do? We have to simply dot product. We have to take the dot product of electric field and the unit vector associated with the area of the given surface. So right here, the electric flux density, that is the flux density per unit area. So the electric flux density, electric flux density through the given surface is phi divided by, phi is the total flux. If A is the total area, then this we have to calculate flux per unit area, and this will be simply given electric field and the dot product of unit vector associated with the area. So we know the electric field. What we doesn't know at this point, the unit vector associated with the area of the given surface, that we have to calculate. So now we have the equations of this plane surface, equations of the plane surface. So we can write this way. Let's say some scalar constant. Let me write it psi is equals to ax plus by plus cz minus d. And now if we take the gradient and if then divided the gradient of this psi, that will give us actually a unit vector, and that unit vector will be the normal to this given surface. Given surface. So right here, therefore the unit vector associated with the given surface a cap will be grad of psi divided by mod of grad of psi. Grad of psi. So when you do this calculation, what will get? You will get a I cap plus bj cap plus ck cap plus ck cap. This will be the gradient of this psi, and then you have to divide it by its magnitude. So what will be the magnitude? Magnitude will be under root of s square plus b square plus c square. Okay, so this is the unit area vector associated with the given surface. So now what will be the flux density? Therefore flux per unit area is equals to electric field. So you have to put the value of electric field here and this value of unit vector here. If you put it here, what we'll get? We'll get a alpha I cap beta j cap plus gamma k cap, and then we have to take dot product with this unit vector ai cap bj cap plus ck cap divided by under root of s square plus b square plus c square. Okay, so when you take dot product, what you'll get? You'll get simply I with I give you 1, j with j give you 1, k with k cap with k cap will give you 1. So what we'll get here? We'll get a alpha plus b beta plus c gamma divided by under root of s square plus b square plus c square. Okay, so this will be the flux density through this given surface. Then what will be the correct option? Correct option will be option A. Correct option will be option A. Okay, so this first case is super easy. If you have a uniform electric field, if you have an open surface, and if we want to calculate the flux, total flux, then what we have to do? We have to simply take a dot product of electric field and the total area of the given surface. That will give us the total flux. And if we are interested to calculate flux density, then what we have to do? We have to simply take the dot product of electric field and unit vector associated with the area. Area vector. Okay, so this is case 1. Now take a look on case 2. Right here, case 2. Case 2, again, let's say given uniform, we have a uniform electric field. Uniform electric field. Plus closed surface. Previously it was an open surface, now it's a closed surface. Plus a closed surface. We have a uniform electric field plus a closed surface. Then how we can calculate the flux? How we can calculate the flux? So let me draw a simple figure. Let's say this is a any arbitrary closed surface. So an arbitrary closed surface. Now if we place this closed surface in a uniform electric field, like this, so let me just draw a few lines here. Yeah. Okay. So this is a uniform electric field will be represented by a set of parallel lines. So this is a uniform electric field, and we have a closed surface. And we have a closed surface. Now, when we have this any closed surface, it could be a spherical surface, it could be a cylindrical surface, it could be a cubic surface, or it could be a cone, any kind of 3D surface, which includes some volume. So in this case, it's a closed surface, and we have placed this closed surface in a uniform electric field. So for this type of situations, what you will notice that you see on the left side of this surface, the left side, I mean some portion like this portion, through this portion you will see the field lines are entering into the surface, and also on the other side of the surface, what you will notice that here, what you can see here, the same number of electric field lines is also leaving the surface. So when we place any closed surface in a uniform electric field, what we'll notice every time we'll see this type of situation. The number of electric field lines that will enter into the surface, same number of field lines will also leave the surface. Will also leave the surface. And in general, when a flux enter into the surface, we take its negative, and when a flux goes out from the surface, then we take it positive. So in this case, if the flux in and flux out both are equal, then what will be the sum of these two? Sum of these two will be 0. There will be no net flux. The amount of flux that will enter, the number of field lines that will enter into the surface, the same number of field lines will also leave the surface, irrespective of volume, irrespective of shape. Either it could be a cylinder, it could be a sphere, it could be a cubic surface. Every time you will see the same thing if we place this closed surface in a uniform electric field. Through some portion of the surface, you will see the electric field lines will enter, and through some portion you will see the electric field line goes out. But if you calculate the flux in and flux out, that means the number of field lines entered into the surface and the number of field line leaves to the surface, these two number will be always same. So in this case, flux in, flux out, they will be same. So total flux will be 0. Okay, so let me write the statement here first. So right here, the net flux is the net flux through a closed surface. The net flux through any closed surface is it's always 0 when it is placed in a uniform electric field. Okay, uniform electric field, and that we can understand this figure. We can understand this figure. You see, in this case, the number of field line that is entering to the surface, the same number of field line is also leaving from the surface. So in this case, net flux will be always 0. If net flux is 0, so net flux is 0. When you say net flux, mean in this case, flux in plus flux out, this will be 0. And from there we can write flux out is equals to minus of flux in. They will have opposite sign. If flux in is negative, then flux out will be positive. Automatically, it's already there of a negative sign. And you will see when flux is entering into the surface, the area vector, if it's closed surface, then area vector will be always out of the surface. And if flux is entering into the surface, so area vector and electric field, they will be opposite to each other. So that's why usually flux in becomes a flux in is always is negative. So flux out will be automatically, let's say, positive quantity. Okay, and also sometimes if it is like a flux out and flux in, we'll see like let's say we have a hemispherical surface, this case. So in this case, you see it is also enclosing some volume, so it will also be closed surface. So in this case, we can see two type of surfaces there. One is flat surface, one is curved surface. So again, if we place in a uniform electric field, if we place this surface in a uniform electric field, then also we can say the total flux will be 0. For that, we can write also the flux through the flat surface and flux through the curved surface, that will be 0. So if we have this kind of situations, we can write flux through the flat surface plus flux through the curved surface, that is the net flux. And if it is placed in a uniform electric field, then total flux will be 0 again. Total flux will be 0 again. So from here also we can write what will be the flux through the curved surface, that will be exactly equal, magnitude will be equal and sign will be opposite to each other. Flat surface. Flat surface. Okay. So sometimes examiner asks what will be the total flux when we place a closed surface in a uniform electric field. Answer will be always 0. And sometimes we need to use this concept. Instead of, let's say, if we place like this surface, or let's say we have a hemispherical surface, this if we place in a uniform electric field, and then examiner asks what will be the curved flux through the curved surface. So though the electric field is uniform, but still this area is curved surface. So if this area is curved, then at different point electric field and area vectors will make a different angle with each other. So because of that, we cannot write the total flux will be the flux into total area. It will be different. We have to do the surface integral. But this type of situations, if we calculate the flux through the flat surface, since it's a flat surface, and so it will be applied as an open surface, and we have already learned how to calculate flux through open surface. We have to simply take a dot product of the electric field and the total area of the flat surface, and that will give actually the total flux through the flat surface. And then using this idea, the curved surface equals to flux through the curved surface will be equals to the flux through the flat surface. From here we can calculate the curved surface without any difficult integration. Okay, so let's solve example here related to the second case. So this is the first question associated related with the second question, second case, where it is written a cylindrical of radius r. Let's say cylindrical surface of radius r with right side cut at an angle 30 degree as shown in the figure is kept in a uniform electric field with its axis along the directions of electric field. The total flux linked with the entire cylinder is. So in this case, what has been said here, let's say we have a uniform electric field. So this is the uniform electric field. And then we have a cylinder whose radius, whose axis is parallel to the given electric field, and it has a radius capital R. Radius capital R. And right side is it's not the of 90 degree. I mean, usually we draw a cylinder like this. We draw a cylinder like this, but in this case, the right side of the cylinder is cut an angle, so it's make like this. It's make like this. So when it is like this means this curve, a flat surface. Nature of the flat surface, actually in this case both are circle. This surface and this surface is circle. But if you cut, I mean if you cut at 90 degree, then it will be a circle. But if you cut other than 90 degree, then it will not be no more circle. It will be actually ellipse. Ellipse. So now what has been asked, if we place this cylinder in this uniform electric field, then what will be the total flux? So again you see what has been written about this electric field, given electric field, it's a uniform electric field, and this is a closed surface. It's enclosed some volume, so it's a closed surface. So according to second situation, if we place any closed surface in a uniform electric field, what will be the total flux? Total flux will be always zero. Total flux will be always zero. So in this case, we have placed this closed surface in a uniform electric field, so net flux will be zero. Net flux through the cylinder will be zero. So what will be the correct answer? Correct answer will be option A. Correct answer will be option A. But sometimes examiner asks what will be the flux. Examiner may ask what will be the flux through the flat surface, through the curved surface, or maybe ask what will be the flux through this flat surface, and through this surface, and through the curved surface of the cylinder. Curved surface of the cylinder. So in this case, we can calculate flux through the each surface. Each surface. So for this question's answer is A. Just for extra information, what we are trying to do here, we are trying to calculate flux through the different surface. So if we want to calculate flux through this curved surface of the cylinder, that's mean through this surface, and through this surface, what will be the flux? So it's a uniform electric field. All over the surface, electric field is constant. And then if we want to calculate the flux through the curved surface, what we have to do? We have to take an elementary area. We have to consider a elementary area. So when you take an elementary area on the curved surface of the cylinder, it will be always radially outward. Directions of this area, it will be radially outward. And in this case, the given electric field is parallel to the axis. So everywhere electric field will be parallel to the length. So it will be like this. So on the curved surface, everywhere electric field and the area vector, they will make a 90 degree angle with each other. So because of that, the flux through the curved surface will be zero. Flux through the curved surface in this case will be zero. Flux through the curved surface in this case will be always zero. If electric field is parallel to the axis of a cylinder, and if say uniform electric field, then everywhere through the flux surface through the curved surface, flux will be zero. Now if we want to calculate flux through this surface, through this surface, since we have already noticed here the net flux will be zero and flux through the curved surface is also zero, then what we can say, the flux of the flux through the curved surface plus the flux through the flat surface, that will be the net flux. So in this case, net flux is 0. So this curved surface plus flat surface, that should be 0. Now curved surface is also 0. So that simply suggests that the flux through the flat surface will also be 0. Flat surface will also be 0. So that means whatever the flux will enter to the left surface through this surface, whatever the flux enter into the cylinder through this surface, the same amount of flux will leave from this surface. Will leave from this surface. So flux through the both surface will be same. Flux through the both surface will be same. So in this case, if we calculate the flux through this surface, we can, without any calculation on this surface, we can say that the flux through this surface will be the same. Only the sign will be opposite. In this case, for this surface, flux will enter into the surface, will take it as a negative, and then flux this surface will goes out, so we'll take it's a positive. Okay. So then what will be the flux through this surface, right surface of the cylinder? So flux flat surface is 0. Now I am writing right. Right means right plus left. Flat left. This sum must be 0. So in this case, if we want to calculate flux through the right surface, then what we have to do? First we have to calculate the area vector of this ellipse, and then we have to take the dot product of electric field and this area vector, area vector of the ellipse. So for that, first we have to calculate area vector of the ellipse. For that, we have to calculate the axis of length of the major axis and length of the minor axis, and then we have to if it's a length of the major axis is A, length of the minor axis is B, semi-major axis and semi-minor axis is A and B. Then what we have to do? We have to simply take the area of the ellipse will be pi AB, and then we have to take the dot product with this electric field. But without calculating this area of this loop, simply but looking at the flux through the left surface, we can also calculate, using this idea, we can also calculate what will be the flux through the right surface. What will be the flux through the right surface? So in this case, we can say the flux flat surface, and which is at the right side. So right side will be the minus of flux through this surface, left surface of the cylinder. Now what will be the electric field? What will be the flux through the left surface? So in this case, you can see here the electric field is going along this direction, left to right, and if it is closed surface, then we have to take area vector on the flat surface in this direction. So in this case, electric field and area vector will be opposite to each other, and it's a circle of radius r. So what will be the area of this part? It will be pi r square. Pi r square, and electric field is uniform, so simply we will write the total flux will be pi r square into E, and their directions are opposite to each other, so it will be negative. And when you take this quantity towards to the right side, what we'll get already one negative sign. So one negative sign will be here, and then when you take a dot product of electric field and area of the left side surface, that will also give you another negative sign. So minus E naught minus E pi square. So ultimately, what will be the flux through the right surface then? It will be plus E pi r square. Plus E pi r square. Okay. So this type of questions also you can solve easily. If you get in this case examiner asks, in this questions it asks only what will be the total flux. So in this case total flux will be 0, but sometimes also examiner may ask what will be the flux to the right surface or to the left flat surface or to the curved surface of the cylinder. So for this type of situations you can use this idea that if we place a closed surface in a uniform electric field, the net flux will be 0. So in this case somehow the total flux in and the total flux out, they will be opposite to each other and their magnitude will be equal. So from there you can calculate the flux to the left surface and right surface. Okay, now take a look on second example. So here it is written a electric field E is equals to alpha I cap, beta j cap, gamma k cap exists in a space. The electric flux through the curved surface of the hemisphere shown in the figure is. Okay, so in this case again we have a hemispherical surface, it's a closed surface, and then we have a uniform electric field. You see electric field is alpha I cap, beta j cap, and gamma k cap, or alpha, beta, gamma. Again it's a constant, it's not a function of x, y, z. So in this case given electric field is uniform and it's a closed surface, so what we can write, total flux will be 0. Total flux will be 0. So you have placed a closed surface in a uniform electric field. Or you can simply write a closed surface is placed in a uniform electric field, so total flux will be 0. Closed surface is placed in a uniform electric field. Uniform electric field. Therefore, the net flux will be 0. Net flux will be 0. And when I say net flux means in this case, see, it's have two kind of surface. One is a curved surface and one is flat surface. So this is the flat surface. If you consider only this flat surface, it will be applied as an open surface. And then we have a curved surface. We have this curved surface. So what we can write here, flat surface plus flux through the curved surface, this is equals to 0. This is equals to 0. So in this case what we have to do, we have to calculate electric field through the curved surface. So electric field through the curved surface can be written as minus of electric flux through the flat surface. Electric field through the flat surface. And you see, if we consider only this flat surface, so we have a uniform electric field, and if we consider only this flat surface, it will be like this. It will be a circle of radius r. It will be a circle of radius r. So what will be the total area? Total area will be pi r square. Pi r square. And since it's a closed surface, I mean complete surface is closed, so if we want to write the directions of the area vector on the flat surface, what we have to do, we have to draw an outward normal. So in this case outward normal will be downward. So according to figure, upward directions, let's say this is the origin, and then this one is y, this one is x, and upward directions is z. So in this case downward will be minus k cap. Minus k cap. So we have an area vector of the flat surface, that is pi r square minus k cap, and we have a uniform electric field alpha I cap, beta k cap, and gamma k cap. So what will be the flux through this curved flat surface then? It will be simply electric field and dot product of the area of the flat surface, which will be pi r square minus k cap. pi r square minus k cap. So from here, when you take the dot product, you will get actually the flux through the curved surface. So what will be the flux through the curved surface? So it will be, when you take the dot product, electric field and this area vector, what we will get? Electric field is alpha I cap, beta j cap, and gamma k cap. And the area have only k components. So k component will give you 1, or other term will be 0. So we'll have a gamma pi r square into E. Gamma pi r square, that will be the magnitude of the flux through the flat surface. And then this negative sign and this negative sign, they will give you positive. So ultimately, the flux through the curved surface will be gamma pi r square. Gamma pi r square. So that will be the total flux through the curved surface. Total flux through the curved surface. Then what will be our answer? It is written gamma pi r. So our answer will be again 1. Okay. Answer will be 1. Okay. So I hope you understood how to use this concept when you place a uniform electric field, when you place a closed surface in a uniform electric field. So in this case, if the examiner asks you total flux, then always without checking anything, if you somehow understood that electric field is uniform, surface is closed, then total flux will be always 0. And if examiner asks you like this type as we have solved here, the electric flux to the curved surface, only some portion of the surface, then you can use this concept to calculate the flux. Okay, calculate the flux. Okay, now then take a look on the third case. So in third case right here, case 3, now instead of electric field, if examiner give us charge distribution plus a open surface. So write here charge plus open surface. So now we have a charge plus open surface. Charge distribution plus open surface. Then what we have to do? So if you have some kind of charge distribution, and then if you have an open surface like this open surface, and if we want to calculate what will be the flux through the surface because of this charge distribution, then what we have to do? First, we have to calculate the electric field. First, we have to consider any point on this given surface. And then what you have to do, you have to calculate the electric field because of this charge distribution. Because of this charge distribution, let's say electric field will be along this direction. And then what you have to do, you have to consider a elementary area around this this point, and let's say area is along this direction. And then you have to take the dot product of these two electric field and the elementary area vector, and then you have to do this integration over the surface. Over the surface. So extra step what you have to do here, if instead of electric field, if examiner give you some kind of charge distribution, either it could be a point charge or it could be a continuous charge. So for that, first what you have to do, you have to consider one point on the surface, and then at this point you have to calculate the flux electric field because of this charge. And so once you know the electric field, then what you have to do, you have to take the dot product of this electric field and this area vector, and then you have to do the surface integral over the surface. That will give you the total flux. Total flux. So let's solve some problem here. Then you will be able to understand how to solve this type of problem. So this is an example of third case where you have to calculate flux of electric field through a circle of radius r is placed in the xy plane with its center at the origin due to a point charge is placed at 0, 0, d is. So in this case, what has been asked, we have a circular loop, like this is the circular loop, have this circular loop of radius r in xy plane, whose center is at origin, and we have a point charge at 0, 0 d means on the z-axis at a distance d from this circular loop. Then it has been asked what will be the flux through this circular loop. Flux through this circular loop means through this area. So you see this is open surface. So this is open surface, and instead of electric field, examiner give us actually point charge. That's mean charge distribution. Point charge. So now we have a charge and we have an open surface. So you have to learn how we can calculate this type of situation. So for that, let me draw this figure again here. This is the circular loop. This is the center. And this is y-axis. This is x-axis. And this is z-axis. And this is z-axis. And we have placed a point charge at 0, 0 d means on the z-axis at a distance d from the center of the loop. Center of the loop. Now what you have to do, you have to calculate the flux through this circular loop. So as I told you here, that if we want to calculate for this type of situations where instead of electric field, if we have some charge distribution and we have an open surface, first what we have to do, we have to consider a point on the given surface. So in this case, let's consider a point here. Consider a point here. I am taking this point at a distance r from the center of this small r, from the center of the circular loop, and making an angle. It's a phi, or in this case we have to write flux as a phi, so write it as theta, making an angle theta with the positive x-axis. Positive x-axis. Then polar coordinate of this point will be r theta. This distance is r and this angle is theta. So polar angle of this point will be r theta. And now if I want to write this in terms of rectangular coordinate, then what will write? What will be the coordinate of this point? It will be r cos theta, r sin theta. And since this point is on the xy plane, because this point is on the loop of the circle and loop lies on the xy plane, so in this case it will be r cos theta sin theta and 0. This will be the coordinate, rectangular coordinate of this point. Okay. Now what we have to do, I have to consider the elementary area around this point. So how we can write the elementary area? In this case, we can write in terms of r and theta. So what will be the elementary area? In 2D polar coordinate system, we write as a r dr d theta. So elementary area ds, I'm writing here ds, can be written as r dr d theta. R dr d theta. And then what we have to do, first we have to write the electric field because of this charge. Electric field because of this charge at this point where we have considered elementary area. So we have a point charge q and we want to calculate the electric field, the point we have considered the elementary area. So for that what we have to do, we have to calculate the length of this side. Length of the point we have considered but distance of the point we have considered elementary area from the point where we have placed this point charge. So what will be this distance? This distance we can simply write, so this distance is r and this distance is d, so it will be under root of r square plus d square. Under root of r square plus d square. So then what will be the electric field? Let me just define it this way. Let's say this point is P. This point is P. And this point is, let's say, some point, let's say Q point. Or Q is the charge, so let us write a S point. S point. So what will be the electric field at point S? Point S, that is where we have considered the elementary area. And then if we know this electric field, then we have to take the dot product of this electric field and the area vector, and that will give you the total flux to this elementary area. And if we do the surface integral over the surface, that will give us the total flux. Okay, so for that, what we have to do here, first we have to write the electric field here, and then already we have considered the elementary area. Now it's the open surface, so either we can take area vector, directions of area vector upward or downward, and in this case, since electric field will be along this direction, so we can take area vector downward. So this is the directions of area vector, and if we place a charge Q here, then electric field will be along this direction. Electric field will be along this direction. Okay. Now let me write this angle, let's say alpha. So if this angle is alpha, then what will be this angle? This angle will also be alpha. So this is the angle at point S between electric field and the area vector. Area vector. So now let me write here the net, the flux through the elementary area ds on the circular loop, or simply write this way: the electric flux. The electric flux through the circular loop due to the point charge Q is flux phi is equals to, what we have to do, first we have to calculate the electric field at the position where we have considered elementary area ds, and then we have to take the dot product, and after taking the dot product we have to integrate over the surface of the circular loop. So then what will be the electric field at this point? Because of this Q point charge, it will be Q divided by 4 pi epsilon naught square of the distance. So square of the distance will be small r square plus d square. So this is the magnitude of electric field, and then magnitude of elementary area. Magnitude of elementary area is r dr d theta, and then the angle between them at this point is alpha, so it will be cos alpha. Okay, so this will be the dot product, and then we have to do the integration over the loop. But in this case, we have to integrate with respect to r and respect to theta, but this alpha, in this case you can see, if we consider this point here, then alpha will be different. So alpha is a function of r and theta. Function is the function of basically r. It's a, if you take a particular theta and then if you make different r, it will be different. But for different theta, maybe for a particular r, it will be always same. So you can say in this case alpha is function of r. So then what will be the value of cos alpha? What will be the value of cos alpha? So we have to write this cos alpha in terms of r. So if we want to write cos alpha in terms of r, what we can write here? Let me write all other term here first. Q r dr d theta divided by 4 pi epsilon naught r square plus d square, and now we have to put the value of cos alpha. So what will be the value of cos alpha in terms of r? So we can write r divided by under root of r square plus d divided by under root of r square plus d square. R square plus d square. And then total flux, what we have to do, we have to do the surface integral over the surface of this loop. So for complete loop, the limit of small r will be 0 to capital R, and the limit of theta will be 0 to 2 pi. 0 to 2 pi. So since there is no theta term, only we have to integrate d theta. So integration of d theta will be theta, and then if you put upper limit and lower limit, what we'll get? You will get 2 pi. So we can write q into 2 pi, and also d is constant, so you can take it outside, d divided by 4 pi epsilon naught, and then we have to do this integration 0 to capital R into r dr, and then in the denominator it will be r square plus d square whole to the power 3 by 2, whole to the power 3 by 2. Okay, so now to calculate the total flux through this circular disk, through this circular loop, what we have to do? We have to do this surface integral. We have to calculate the integration. So let me just write here. So total flux phi. But before that, let me just simplify this term. You say 2 pi will cancel out from denominator and numerator. Then what we'll get? We'll get qd divided by 2 epsilon naught. Qd divided by 2 epsilon naught, and then we have to do this integration 0 to capital R dr, and then r square plus d square whole to the power 3 by 2. So you have to do the integration of this term. When you do the integration of this term, what you'll get? I think few days ago we have done similar type of integration. Exactly same integration, not same, exactly same integration. So what will be the value of this integration? It will be simply minus 1 by under root of r square plus d square, and then we have to put the upper limit and lower limit. So lower limit is 0 and upper limit is capital R. So when you do that, finally what you'll get? You will get qd divided by 2 epsilon naught. When you put a lower limit, you have to put a negative sign, so this negative sign will be plus. So then we'll get 1 divided by d, 1 divided by d minus 1 divided by under root of capital R square plus d square, capital R square plus d square. And if you multiply this d with the bracket term, what you'll get? You'll get finally q divided by 2 epsilon naught 1 minus d divided by under root of r square plus d square, r square plus d square. So that will be the total flux through this circular loop because of this point charge. And again, just for, from the point of view of competitive exam, if you are going to attend any kind of competitive exam where you have to solve at least, if I talk about, let's say, JAM exam, we have to solve 60 questions in 3 hours. If we let's say NET exam, almost we have to solve more than 40-45 questions in 3 hours. So it's always recommended that if we can remember some standard result with a figure, then it will be very, very easy for us. Otherwise you have to do this integration and then finally you'll get this result. That will take a long time. So what you can do, you just do like this way. Let's say we have either circular disk or circular loop of radius r, and then if we place a point charge at a distance d on its axis, let's say charge is q, then the total flux through this circular loop, will be always q divided by 2 epsilon naught 1 minus d divided by r square plus d square, r square plus d square. Okay, I think if you practice 2-3 times, you will remember, you can remember these things. Okay. q divided by 2 epsilon naught 1 minus d divided by r square plus d square. Now let me give you one amazing point. Okay, so right here note, you see we have a circular disk or circular loop of radius r, and we have placed a charge at a distance d on its axis. Now in this case, if I put this r tends to infinity, that's mean if I make the radius of this circular loop infinite, then what will happen? This circular loop will behave like as a infinite plane. So if we put r tends to infinite, means r almost is infinite, then what will happen? This circular loop, now it will behave like as a infinite plane. Infinite plane. And then in front of this plane, if you plane at any distance, if you place a point charge q, what you will see, if you put this if you put the value of r in this result, r tends to infinity, what you will get, flux through this loop will be q divided by 2 epsilon naught. When you put r tends to infinite, this term will be 0, this term will be 0. So if this term is 0, then flux will be q by 2 epsilon naught. So it will be independent of distance of the point charge from this plane. And this loop will now behave like as a infinite plane. Infinite plane. So that's mean if we place a point charge in front of a infinite plane, then what will be the total flux through this surface? It will be q divided by 2 epsilon naught. Q divided by 2 epsilon naught. Okay. So you see, if you remember this result with this figure, in this case the flux through this circular loop will be phi is equals to q divided by 2 epsilon naught 1 minus d divided by under root of r square plus d square. If you can remember this result, then you can easily calculate the flux through this plane surface. What will be the flux through this plane surface? In this case, if we place a q charge in front of any infinite plane, so what you have to do, you have to put this r tends to infinite. When you put the value of r equals to infinite, this term will give you 0 and you get q by 2 epsilon naught. Q by 2 epsilon naught. So that will be the flux through this plane. If it is positive charge, then electric field will goes like in this way. So in this case, flux will goes upward to downward. Flux will go from up to downward. Okay. And also, why I'm saying that if you remember this result, we can also use this result for other cases. For other cases, I think, yeah. So let's say, let me give you one more example where you can use this result directly. But for that, we need to, I will come back again this problem after some times. There also we can see, if we remember this result, then we can easily calculate for flux for other different kind of situation. We'll come back that point after some times. Okay, at this point, you just remember these things. If we have a circular loop, and if we have a circular loop of radius r, and if we place a point charge q at a distance d, then we can write the total flux through the circular loop will be q by 2 epsilon 1 minus d divided by under root of d square. And if you make r tends to infinity, that's mean this plane, the circular loop will behave like as a plane. And in this case, we place a charge at any distance from this circular loop, from this infinite plane, then flux through this plane will be q by 2 epsilon naught. Q by 2 epsilon naught. Okay. Then based on this, whatever we have learned here, so from there you can solve this problem where it is written here. What is written here? The charges q and 2q are placed at minus 1 0 0 and 1 0 0 respectively. The electric flux through the x equals to 0 plane. X equals to 0 plane. So let me draw the figure first. So let's say this is x-axis. So x equals to 0 plane means so yz plane. Okay, if this is x-axis, let's say this is y-axis and this is z-axis. Okay, so what we have to do, we have to calculate the flux through this. This surface, x equals to 0 surface. X equals to 0 surface. And where the charge is placed at x equals to, so this is x equals to 0 surface. That's in xy plane, a yz plane, and then we have placed a point charge here. The charge is q. So x equals to -1, we have a point charge q. So this one charge is here, and another charge is x equals to plus on the right side of the plane here, and this charge magnitude 2q. Okay, 2q. Then what has been asked, what will be the total flux through this x equals to 0 surface to the yz plane? So again, it's a yz plane, it's an infinite plane. So we can calculate the flux because of each charge using this idea. If we place a point charge at a distance, any distance from an infinite plane, then flux through this plane will be q by 2 epsilon naught. Q by 2 epsilon naught. So we have a point charge here. It's a positive charge, so electric field line will goes along this direction like this. So flux will goes from left to right, and what will be the flux because of this charge? It will be q divided by 2 epsilon naught, total flux. Because of this charge, the total flux that will pass from left to right, it will be q divided by 2 epsilon naught. And also we have another charge 2q on the right side of the plane, and it's also positive charge, so it will create an electric field from right to left. So because of that, the net flux, it will goes left to right direction, right to left direction. And what will be the total flux in this case? Total flux, like electric field line will goes like this way, like this way. So total flux towards the right, towards the left. What will be, this is the total flux towards the right because of this charge. And what will be the total flux because of this 2q charge? It will be according to this definition. According to this definition, one can write q divided by 2 epsilon naught, but for second case the charge is 2q, so itself it will be q divided by epsilon. Q divided by epsilon. Then what will be the net flux? Flux through the x equals to 0 plane. What will be the flux through the x equals to 0 plane? So it is q divided by epsilon, which will pass through towards left, minus q divided by 2 epsilon, it will pass towards right. So net flux will be subtraction of these two flux, because they are opposite direction to each other. They are passing through opposite direction to each other. So in this case, total flux will be q divided by 2 epsilon naught. Q divided by 2 epsilon naught, that will be the net flux through this plane, and net flux will be towards left. Towards left, because this flux is larger compared to this flux, so that's why the net flux will be towards the left. And what will be the net flux? Q divided by 2 epsilon naught. Okay, so we got some idea. If we have a charge distribution plus open surface, how to calculate the flux. Now consider the case 4. Case 4, when we have to calculate flux because of charge distribution plus a closed surface. So if you have a charge distribution plus a closed surface, then how we can calculate the flux? So right here, charge plus closed surface. Charge plus any closed surface. Okay, this is the scenario of case 4. So if you have some charge distribution and if you have any closed surface, then how we can calculate the flux through this closed surface? It's through the closed surface. So in this case, one law we can use, and this is called Gauss law. Gauss law. So let's say we have any closed surface like this. Say any closed surface. It's enclosed some volume, and let's say inside we have placed a point charge Q. Point charge Q. Now this Q, it will create an electric field. Will create an electric field, and associated electric field lines we can draw like this, as we have learned in the last class. So you see this field line will passes through the surface. That's mean there will be some flux through the surface. The surface. Now we have to calculate what will be this flux. So in this case we have a charge, we have a closed surface. Now in this case we can use Gauss law. So what has been said in Gauss law? Let me just write first the statement of the Gauss law, and then we'll come back to this point again. We'll try to prove how we can calculate total flux for this case. We'll try to calculate what will be the total flux. So what has been said in Gauss law, that if we place the net flux through any closed surface, will be always 1 by epsilon naught times charge enclosed by the surface. Charge enclosed by the surface. So write this statement here. But before that, write a Gauss law. So what has been said in Gauss law? The net flux through a closed surface, let me just write it this way. The net flux through any closed surface, is 1 by epsilon naught times charge enclosed by the surface. Charge enclosed by the surface. Charge enclosed by the surface. So if I, let's say at any point, because of this charge on the surface, electric field is E, and in this region elementary area, let's say ds, then we can write this statement of Gauss law in mathematical form. E dot ds, that will be the flux through this elementary area. Since it is then the total flux of the surface will be then so E dot ds, this is the flux through this elementary area, and if you want to calculate total flux through this surface, then we have to do the surface integral. But in this case, since it is a closed surface, so we have to take a closed surface integral, is equals to, it will be 1 by epsilon naught times Q enclosed by the surface. Q enclosed by the surface. So this is the statement of Gauss law. Okay. So electric flux through any closed surface will be always 1 by epsilon naught times charge enclosed by the closed surface. And this I think we can easily prove by doing few steps of mathematics. So let's just write here proof. So for that, just take a look on the figure. So let's say this is any closed surface, and we have point charge. We have placed a point charge Q this side, and let's say because of this charge at a distance r from this charge at this point, electric field is at any point inside the volume. At this point, let's say electric field is E. Electric field is E. Or we can say the surface. Better, you can just say same way. You can write this electric field at a distance r from this point charge here. Let's say E. Then what we have to do in order to calculate the flux through this closed surface, phi is equals to, we have to take the dot product of this electric field with the elementary area, and then we have to do the surface integral. But in this case, surface integral will be closed surface integral, because surface is closed. Now, according to divergence theorem, we can convert this surface integral into a volume integral. So for that, what we have to do, first we have to take the divergence of electric field. So whatever the electric field, it will generate this charge inside the volume into dV. Okay, but this V is the volume that is enclosed by the surface, inside the surface. So now, what will be the electric field at any point inside this volume or inside the surface? If we consider any point at a distance r from this charge, what will be the electric field at this point? So we have to take the divergence of this electric field, which will be Q divided by 4 pi epsilon naught r cap divided by r square. R cap divided by r square, and then we have to take the volume integral. Here, this r is not on the surface, because we have to take the volume integral. When we convert the surface integral into volume integral, that's mean this point usually lies inside the volume at any point, at any random point, but it must be lies inside this surface. So inside the surface at any point, electric field can be written like Q divided by 4 pi epsilon r square into r cap, where r is the distance from the point charge. And now if we take the divergence of this vector, what we'll get, we can write Q divided by 4 pi epsilon naught outside, and then what we have to do, we have to take the divergence of this vector r cap divided by r square into dV. What will be the divergence? We have already learned these things. If we take the divergence of a vector r cap divided by r square, we can write in terms of Dirac delta function. So the divergence of this vector will be 4 pi to Dirac delta function at the position of charge, okay, into dV. So now 4 pi will cancel out, and then what we'll get Q divided by epsilon naught, and then dV into 3-dimensional Dirac delta function. So what we have to do, we have to take the volume integral of this Dirac delta function over the volume. And where we'll get this Dirac delta peak, it is the position of this charge, and since charge is inside the volume, so this Dirac delta peak will also be inside the volume. That means this volume integration will give us 1. If the volume integration give us 1, then what will be the final result? It will be Q by epsilon naught. Okay, so see what we have written here, exactly we are getting the same result. We have calculated flux, and that flux will be, in this case, the Q charge is placed inside the volume, so Q divided by epsilon naught, that is the total flux. Okay, so if we have a closed surface and we have a certain kind of charge distribution, so in this case, what we have to do, if we want to calculate the flux, we have to only calculate what will be the enclosed charge by the surface. If we know the enclosed charge, then flux through the closed surface, we can write Q divided by epsilon. If there is no charge inside the surface, then enclosed charge will be 0, so flux will also be 0. Flux will also be 0. If charge does not lies inside the volume, then electric field will also be 0. Flux will be 0. Flux will be 0 through this closed surface. Okay, so see, this is written in terms of integration form. E dot ds surface integral equals to Q by epsilon naught. Sometimes we also need to write this. I mean, if you do this thing, like if we have some charge distribution, but we want to calculate the flux, so what we have to do, we have to simply enclose charge instead of electric field. In this case, we will find out what will be the charge inside, and we can calculate the flux. Now, instead of electric field, if examiner give you instead of charge, if examiner give you some non-uniform electric field, and then if he asks you what will be the flux through this closed surface, what you can do, if you know the electric field, again you have to do the surface integral. But the main thing you will miss here, if you have an electric field, if you do the surface integral, you will get the resultant flux through this surface. But if you are getting the resultant flux through this surface, that means there will be some enclosed charge, but you will never get the information doing this surface integral how the charge is distributed inside the volume. So if you want to see how the charge is distributed inside the volume, then what we have to do, we have to write this Gauss law in terms of differential form. This is the integration form of Gauss law. If we write in differential form, there you will see we'll get some relations between electric field and the charge density. Because of that, this electric field will generate. So from there you will get idea how the charge is distributed over the volume, and because of that you can calculate also what will be the total flux. So keep that in mind. Let me write here also the differential form of Gauss law. This is the integral form of Gauss law. This is the integration form of Gauss law. Now let me write a differential form of Gauss law. Differential form of Gauss law. Okay, differential form of Gauss law. So for that, again consider any closed surface. This is a arbitrary closed surface, and let's say we have some kind of charge distribution here. Now we know also we can how to write this point charge in a continuous charge distribution. So in general, we can write some arbitrary continuous charge distribution is there, and associated charge density, let's say rho. Charge density is rho, and because of this charge there is electric field in this region, and so let's say electric field is E. So then what we have to do, we have to find out the relations between this charge distribution and this electric field, and that we can find out from the differential form of Gauss law. So how we can do that? For that, let me just write the integral form of Gauss law. We know E dot ds through a closed surface is equals to 1 by epsilon naught Q enclosed. Q enclosed. Now we can use divergence theorem, and we can convert this surface integral into volume integral. If we do that, then what we have to do, first we have to take the divergence of electric field, and then we have to take the volume integral of this divergence of electric field over the volume that will be enclosed by this surface. And on the other hand, enclosed charge can be written like rho into dV. Rho into dV, where rho is any arbitrary charge distribution. Could be uniform, it could be non-uniform, any arbitrary charge distribution. So this will give you total volume inside, total charge inside the volume. So you see both sides, we are taking the volume integral over the same volume, same region, or you can say same volume. So you can remove the volume integral from both sides. Then what we'll get? We'll get divergence of E is equals to 1 by epsilon naught rho. 1 by epsilon naught rho. So this is the actually differential form of Gauss law. Divergence of electric field will give us how the charge is distributed over this region. How the charge is distributed over this region. And then if we want to calculate the charge density rho, so how we can calculate this charge density? just multiply epsilon naught here on the left side, then what we'll get? Divergence of V. So this will give us the charge density associated with any electric field. So once we know the charge density, then we can calculate. We can also calculate the total flux through this closed surface. Will be simply Q enclosed. But we have to take the volume integral of these things, and that will give us the total flux. Once you know the total enclosed charge and the surface is closed, so flux will be Q divided by epsilon naught. Okay. So sometimes we'll use this approach to, if we want to calculate flux through any closed surface, and if we have if we have an electric field, and if we want to calculate the flux through any closed surface, so sometimes we'll use this technique. We'll do simply surface integral, but sometimes it's always better just take the surface volume integral. First calculate the divergence of the electric field. That will give us, using this result, we can calculate what will be the volume charge density. And once we know the volume charge density, then we can calculate the total enclosed charge within the closed surface. And if you know the total enclosed charge, then we can say flux through the closed surface will be Q divided by epsilon naught. So we'll see different situations when the surface integral, when will we use the surface integral, when and what situations we'll use this volume integral. That means first we'll calculate charge density, and then we calculate the total enclosed charge. From there also we can calculate the flux. Okay. So let me just give you some example associated with these two cases. Okay. So this is the first example associated with the fourth case. What is written here? A charge Q is at the center of two concentric spheres. The outward flux through the inner surface is phi, while through the outer surface is 2 phi. The amount of charge contained in the region between two spheres is, okay. So let me draw a figure first here. So what has been written here? We have a true concentric spherical surface. So this is one surface, and we have another spherical surface like this. Yeah, another spherical surface like this. Now, what has been written? The charge Q is at the center of the two concentric spheres. So they have same center, they are concentric. At this point, we have placed a Q charge. We have placed a Q charge. Then what has been said in the question, that the flux through the inner sphere. That means this red sphere is the inner sphere, and white sphere is the outer sphere in this case. So the flux through the inner sphere is phi, where the flux through the outer sphere is actually 2 phi. And it then asks how much charge is contained in the volume between these two spheres. Two sphere. So let me just write in this way. Let's say we have placed a Q prime charge between this region of the two sphere. Now, since both the surface is closed and we have a charge distribution, so we can write according to Gauss law. We can write flux through the inner surface, flux through the inner sphere, it is written phi. In the questions it is written phi, so let me write as phi. So what will be the value of phi? See, according to Gauss law, we can write total enclosed charge within the inner sphere is small q, so we can write Q divided by epsilon naught. Okay, Q divided by epsilon naught. And what will be the flux through the outer surface, outer sphere? Outer sphere. In this case, it is written 2 phi. 2 phi. And according to Gauss law, if I want to write the charge through the flux through the second surface, what you have to do? we have to calculate total enclosed charge. So with respect to the second surface, outer sphere, what will be the total charge? We have a q charge here and we have put q prime charge here. We assume that there is a q prime charge between these two spheres. So total charge enclosed by the outer sphere will be q plus q prime divided by epsilon naught. That will be the flux. Now from the first definition, if I put the value of phi in the second equation, what we'll get? We'll get a 2 into q divided by epsilon naught is equals to q plus q prime divided by epsilon naught. So epsilon naught will cancel out from both sides. What we'll get? Q prime is equals to q. Q prime is equals to q. So that's mean we have placed a q charge between the region in the between the two sphere. Region between these two sphere. Okay, so correct answer will be option A. Correct answer will be option A. Okay. Then take a look on second question. It is written a uniformly charged and infinitely long line having a linear charge density lambda is placed at a normal distance y from a point O. Consider an imaginary surface of radius r with O as a center and r is greater than y. The electric flux through the surface of sphere is. Okay, so let me figure according to the statement of question. Let's say we have a infinitely charged carrying rod like this. Yeah, like this. And then what has been said, the charge per unit length is lambda, so write as lambda, and is located at a distance, normal distance y from the point. Let's say consider a point here. So this is the point, and perpendicular distance of this long line charge is y. This distance is y, this point is O. Okay. Now what has been asked? Consider an imaginary sphere of radius r with O as a center. So now we have to imagine a sphere. The center will be at O, at point O, and radius of this sphere will be capital R, where capital R is greater than y. Capital R is greater than y. So we can draw like this. So let's say this is the center and this is the radius of the sphere. So it will be like this. Okay, so this is a sphere. This is a sphere. So now what we have to do? We have to calculate what will be the flux that will passes through this sphere. Passes through this sphere. So the sphere has a radius r. Now we have to calculate what will be the flux through this sphere. Okay. So for that, let me just draw these 2 points with the center of the sphere. Okay, center of the sphere. So now what will be this distance? Or let me just give a name. This point center is O and this point, let's say A. This point is B and this point is C. Okay. So now what will be the length of OA? It will be the radius of the sphere. So it will be R. So this is R. And also what will be the length of this OB? It will also be R. It will also be R. And then you see from this we have drawn a perpendicular. So OC is the normal to this charge carrying length, charge carrying line charge, sorry, infinitely long line charge. OC is the normal to the infinitely long line charge. So in this case, this angle will be 90 degree and this angle will also be 90 degree. So from these two triangle AOC and BOC, we can say this OA is equals to OB, and this angle C for both triangle is 90 degree, and OC line is common. OC line is common. So then we can say that this length and this length must be equal. These two length must be equal. So then what will be the total length AB? Total length AB will be 2 times of AC. By the way, before solving this question, what is the concept of this question? So we have a line charge carrying wire and we have a closed surface. Now this charge carrying wire is actually passes through this sphere. So some portion of this charge carrying line, this charge carrying line, charge carrying rod or this charge carrying line will lie inside the sphere. So because of that, we can say some amount of charge will be enclosed by the sphere, and since sphere is a closed surface, so once we know the total enclosed charge within the sphere, then we can say the flux will be Q enclosed divided by epsilon naught. So for that, what we have to do, you have to calculate what will be the length of AB. If we know the length of AB, and then we have to simply multiply with lambda, and that will be the enclosed charge. And then if we know the enclosed charge, then flux will be enclosed charge divided by 2 epsilon naught. So for that, first what we have to do, we have to calculate the length of AB. For that, what we can write from the figure, that AB length equals to 2 times of AC, and from the figure, what we can write, how we can write the length of AC. You see this triangle OAC is right angle triangle, where this length OA is R and OC is Y. OC is Y and angle C is 90 degree. So what will be the length of AC? What will be the length of AC? It will be under root of R square minus Y square. R square minus Y square. So this will be the total length of AB, 2 times of R square minus Y square. Then therefore the enclosed charge by the sphere is Q enclosed equals to what? It will be simply lambda into this AB length. AB length 2 times into under root of R square minus Y square. So we can write 2 lambda under root of R square minus Y square. So this is the enclosed charge. So therefore the flux through the surface sphere is phi is equals to, will be Q enclosed. According to Gauss, let's say closed surface, and we know the enclosed charge, so we can write flux equals to Q enclosed divided by epsilon naught, and that will give you 2 lambda under root of R square minus Y square divided by epsilon naught. Divided by epsilon naught, and that will be the flux. So what will be our correct answer? Correct answer will be option B. Correct answer will be option B. Okay, now take a look on third problem. So in this problem, it is written a point charge Q is placed at the center of a cylinder of radius R and length 2L. The electric flux through the curved surface of the cylinder. Again, let me draw a figure first. Let's say this is a cylinder of radius r and length 2l. Length is 2l and radius is r. So let me just draw a axis first. Let's say this is the axis and the radius of the cylinder is capital R. Okay, and now we have placed a point charge at the center of the cylinder. So this is the center. So that's mean on the axis, and at the middle of the length we have placed a point charge Q. Point charge Q. Then what has been asked? The electric flux through the curved surface of the cylinder. Okay. So when you place this point charge inside the cylinder, what will happen? This point charge will create an electric field. This point charge will have electric field, and we can draw electric field line like this way, this way. This way. Okay, so it will create an electric field like this. So you can see here the electric field lines will passes through flat surface as well as curved surface. So we'll get flux through the both surface, flat surface as well as curved surface. So now what has been asked? Then what will be the flux through the curved surface only? Only curved surface. Only curved surface. So since it is a closed surface, it's a closed surface, and we know the total enclosed charge is Q. So we can say the total flux will be how much? According to Gauss law, you can say Q divided by epsilon. That is the total flux. Now this total flux will pass through curved surface as well as flat surface. So we can write here flux through the flat surface plus flux through the curved surface is equals to Q by epsilon naught. Is equals to Q by epsilon naught. And now what we have to do, we have to calculate flux through the curved surface. So curved surface, it will be Q by epsilon naught minus flux through the flat surface. Flux through the flat surface. So now how we can calculate the flux through the flat surface? So you see, already we have discussed a point here. This case, if we place a point charge at a distance d on the axis of a circular loop of radius r, then what will be the total flux through this surface? It will be Q divided by epsilon naught 1 minus d divided by under root of r square plus d square. R square plus d square. So you see, in this case also, if we just consider only this bottom surface, let me just consider only this bottom surface, then how will look this point? We'll see we have a circular surface whose radius is r, and then we have a point charge Q at a distance L on the axis of this circular loop. On the axis of this circular loop. So what will be the flux through this flat surface then? What will be the flux through the flat surface on the bottom surface? It will be Q divided by 2 epsilon naught 1 minus d. In this case we will replace by capital L, because the distance, center of the distance from the bottom surface will be L, because it is placed at the center. So then what we can write here, Q divided by epsilon naught, and then flux through the flat surface will be, let me just write flux through the bottom surface. It will be Q divided by 2 epsilon naught, Q divided by 2 epsilon naught, Q divided by 2 epsilon naught, and then 1 minus d will be replaced by capital L here in this case. So L divided by under root of r square plus L square. r square plus L square. Now in this case, this bottom surface and top surface, they have actually same kind of symmetry. The amount of flux that will pass through bottom surface, the same amount of flux will also pass through the top surface, and both are flat. So in this case, total flux through the flat surface will be 2 times of this surface, flux through the bottom surface. 2 times of flux through the bottom surface. So from here, what you'll get, this 2 will cancel out, and from there you will get a q by 2 epsilon naught, q by 2 epsilon naught will cancel out. So we'll get q by epsilon naught and then L divided by under root of r square plus L square. So this will be the flux through the curved surface. See, so using this result and the concept of Gauss law, we can easily calculate the flux through the curved surface. If you don't want to use this result, then you have to do a difficult integration. First, you have to calculate an electric field because of this point charge on the curved surface, and then you have to consider elementary area on the curved surface, and then you have to take the dot product of these two, and then you have to do the surface integral over the whole curved surface, which will be a little bit complicated. But if you use the concept of Gauss law, and if you use this concept that what will be the flux through the flat surface, and simply just writing the total flux will be sum of flat surface and sum of the flux through the flat surface and curved surface. From there you can easily calculate the flux through the curved surface. And in exam also you will get this type of question where you can use the standard result, and using the standard result you can calculate the flux through this type of curved surface. Okay, just to understanding this point, I mean just to check you have understood or not whatever we have used through whatever concept we have used here to solve this problem. Let me give a homework for you, which will be exactly same type of questions, but you have to do by yourself. Let's say instead of this cylinder, we have a hemispherical surface of radius r. Hemispherical surface of radius r. Now if we place a point charge, let's say its center is at the origin, and this is x-axis, this is y-axis, and this is z-axis. So now if we place a point charge at a distance, let's say r by 2 from the origin, or on the z-axis at any point. The z-axis, consider a point at a distance r by 2 from the origin, and if we place a point charge q, then what you have to do, you have to write the flux through the curved surface of the hemisphere. So what will be the flux through the curved surface of the hemisphere? So you see, if you place this point charge, so it will create an electric field line like this. So because of that, you will get a flux through the curved surface as well as a flat surface. So now what you have to calculate, you have to calculate only flux through the curved surface. Okay, and it will be exactly like whatever concept we have used in these questions. You can use same concept here also, and try to calculate what will be the flux through the curved surface of the hemisphere. Okay, so now this is a next questions associated with the Gauss law. So in this questions it is written a point charge q is placed at 0 0. An imaginary sphere of radius r is centered at 0 0 minus a, where a is greater than r. The sphere starts moving along the z direction, positive z direction, with a constant velocity v0. Then which of the following option for the electric flux through the sphere versus time is correct? Okay, so let me figure first, and then we can solve this problem again. So let me just draw z-axis. Let's say this is our z-axis. This point is z equals to 0, and then we have a point charge a point charge is placed at origin. That's mean 0, 0, 0 here. This is y-axis, this is x-axis, this is z-axis, and we have a place a point charge at 0, 0, 0. That's mean at the origin, at this point. Okay, point charge q at this point. Now, what has been said in the next statement, the imaginary sphere, a spherical surface of radius r is centered at 0, 0, minus a, where a is greater than capital R. So r radius, we have to consider a sphere of radius r, whose center will be at 0, 0, minus a, that is on the z-axis, but at a distance a from the center. However, this a will be greater than r. So we can draw like this. This is z equals to minus a, and let's say draw a sphere like this. Okay, so in this case you can see this distance, this is the r, and this is the distance of the center from the origin. So in this case a is greater than r. This is the distance of the center from the origin, and this is the radius. So you can clearly see from the figure that in this case a is greater than r. Okay, so now we have a sphere like this. So now in next line, what has been said in this question, that if the sphere start moving along the positive z direction with a constant velocity v0, now this sphere start moving with a constant velocity v0 along positive z direction. Positive z direction. Then what will be the variation of flux through this sphere with time? So let me time on the x-axis, and let me write time on the x-axis and flux on the y-axis. So this. Now at t equals to 0, when the center of the sphere at z equals to minus a, the flux will be 0. And then this sphere will start moving upward direction. So because of this, center will shift. So after some times, so until this, let's say this point, so consider this point is C. So until this C point cross the origin, the flux will be, the total enclosed charge through this enclosed by this surface will be 0, because charge is at the origin. So until charge will lie outside the sphere, the total flux through this flux will be 0. But as soon as this charge will come inside the sphere, because this sphere is moving actually, right now it is here, and after sometimes, let me just draw a few other sphere also, other position. After sometimes maybe it will be here, and then after sometimes it will be here, and after sometimes it will be again here. Okay, so at different time the position of the sphere will be different. So what you will see, when the charge will lie outside the sphere, the total flux through the sphere will be 0. But as soon as the charge will be inside, when charge will be inside the sphere, then total flux will be q by epsilon naught, and that will be constant. So you can see that for certain time, when this charge, just the sphere will come like this, at some point sphere will become like this. So at this point, after some times, let's say at t equals to certain time, and then if you change little bit more time, then it will be, sphere will be like this. So charge will be inside the sphere. Charge will be inside the sphere. So flux will be q by epsilon naught. So let me clear this figure again and draw some other figure. Let me just draw 2, 3 sphere. So this is the initial position, and then this sphere will start moving upward. So there will be at a time when just this charge will be inside the sphere. So it will be like this. So at this time flux will be q by epsilon naught. So for some time flux will be 0, and then at a certain point flux will be q by epsilon naught. Q by epsilon naught. And then if the sphere is start moving, and after some times the moving upward, since this sphere is moving upward, so after sometimes what we'll notice that sphere will be just like this. Sphere will be just like this. So again this charge will lie outside the sphere, so again the flux will be 0. But to move the center from here to here, it will take some time. So during this time, total flux will be always, total enclosed charge will be always q by epsilon naught. So flux will also be q by epsilon naught. So it will be q by epsilon naught. And then as soon as this point will cross the origin, then flux will be 0. Okay. Charge will lie outside, flux will be 0 again. So this will be the variation of flux with time. Variation of flux with the time. So correct option will be option D. Correct option will be option D. Simple concept is a closed surface. If charge lies inside the sphere, flux will be q by epsilon naught. If charge is outside the sphere, then flux will be 0. So now initially charge was outside the sphere, so flux will be 0, and then sphere is started moving upward. So after some point, after some times, charge will come inside the sphere. So because of that, flux will be q by epsilon naught. But since sphere is moving upward direction, so the charge will lie for certain time period, for certain finite time period within the sphere. So during this time, flux will be q by epsilon naught. Again, as soon as this point will, origin will, since this sphere is moving upward direction, so after sometimes the lower surface of the sphere will cross the origin. So at that point again flux will be 0. So you will get a figure like this. Flux versus time will give you graph like this. So correct option will be option D. And then this is another question related to Gauss law. What has been said in this question? Consider a two spherical cell of radius r having a uniform surface charge density. Consider spherical cell of radius r having the uniform surface charge density sigma. Suppose we construct a spherical Gaussian surface having same radius but its center shifted from the charged sphere by a distance r. See the figure. Okay. Then what is the total flux E dot ds through the Gaussian surface? So in this case, in the dotted surface is the Gaussian surface, and the solid surface is a uniform charge carrying spherical cell. But both the surface have same radius and their center are shifted by a distance r from each other. So this distance is r. Okay. So now what has been asked, what will be the flux through this Gaussian surface? So we have this Gaussian surface. So what will be flux through this Gaussian surface? Okay. So from this figure, maybe you will not get a clear view. Let me draw two sphere first. Let's say this is one spherical cell like this, and also we have another spherical cell. The center, let's say here. So red one is the Gaussian surface. Okay, this is the Gaussian surface, and both are actually spherical surface in this case, like this. So now this white surface, which is actually charge carrying spherical cell, it's carrying uniform surface charge density over its surface. Then what has been asked, then what will be the flux through this Gaussian surface? Gaussian surface. So in this case, Gaussian surface is actually what is written as a spherical surface. That means it's a closed surface. And since it is enclose some portion of the charge carrying sphere, so it will also enclose some charge. So whatever the charge that is lies within this this portion, this spherical cap portion, spherical cap portion of the sphere, spherical surface, the charge on the spherical surface will actually lies within the Gaussian surface. So we have to calculate the area of the this spherical cap portion, and then charge since uniformly distributed. So once we know the area of this portion, then we can calculate what will be the flux. What will be the flux through the Gaussian surface. Okay. So let me just draw another figure. Maybe from there you will get a clear idea. So you see this portion. This portion will behave like as a spherical cap. Spherical cap. And this portion actually inside this Gaussian surface here. Gaussian surface here. So you have to calculate what will be the area of this portion. Area of this portion. So once we know the area of this portion, then we can simply multiply with sigma, and that will be the enclosed charge within this spherical cap portion on the spherical cap portion, and which will be exactly within this Gaussian surface in this case. Then we can calculate the flux will be the charge enclosed by the surface divided by epsilon naught. That will be the flux. So for that we have to calculate this area of the spherical portion. So how we can calculate this area of this portion? So for that we know the distance between these 2 points is r, and also let me just draw a perpendicular line like this from here to here. Get to here, and if you connect this 2 points here, let's say here, so from this triangle what we can write here? Let's say this is the center of the sphere O, this is the center of the sphere of Gaussian surface O dash, and let's say this is the point where two spheres cut each other. Let's say R point. R point. So this triangle O prime and R, what type of triangle it is? You see the distance of O prime is R. The distance of R, let me write it as a P, because the radius is also capital. So O dash is R, and then what is the distance of OP point? It is also R. This is the point on the surface of the sphere from the origin, so it will also be R, and the distance of the point P from O dash will also be R. So it's actually a equilateral triangle. Equilateral triangle. Then what will be this angle? This angle will be 60 degree. This angle will be 60 degree. So if I compare these things here, let's say this is the z axis. You can consider this is the z axis like this. So then the area that will be inside this Gaussian surface, it will be spherical cap portion like this, where the angle, this portion, this angle is 60 degree. That's mean area that will be inside this Gaussian surface, for that theta will vary from 0. At this point theta will be 0 because that is the z axis. That is the z axis. So theta will be 0. At this point theta will be 0, and then we'll increase the value of theta like this. When it will come at this point, it will be 60 degree. It will be 60 degree. And for, since it's a spherical cap, so we have to calculate the what will be the limit of phi. Limit of phi will be 0 to 2 pi. 0 to 2 pi. So if we want to calculate the area of this spherical cap portion, so how we can calculate area of the spherical cap portion? So that will be, this is we can consider elementary area on the sphere, and then if we integrate over the whole limit like 0 to pi and then 0 to 2 pi, that will give us actually total area of the sphere. But in this case Phi will be vary from 0 to 2 pi, but if we take the variations of theta 0 to 60, that will give us only the area of the spherical part, spherical cap part. So let me just write here the area of the enclosed part of the sphere, the area of the enclosed part of the sphere by the Gaussian surface is how much? Let's say A is equals to, radius is r, so what will be the elemental area? R square sine theta d theta d phi. Now what will be the limit of theta in this case? For this portion it will be 0 to pi by 3, that is 60 degree, and what will be the limit? 0 to 2 pi. You see, for every value of theta we can draw a circle around the z-axis, right? So the limit of the phi will be 0 to 2 pi. So when we do this integration, what you will get? You will get from the phi you will get 2 pi, so 2 pi r square, and when you do the integration of sine theta, it will give you minus cos theta, and lower limit is 0 and upper limit is pi by 3. So cos 60 is half and cos 0 is 1. So finally what we'll get here? 2 pi r square, and integration limit and integration will give you 1 minus half. So you'll get a pi r square. Okay, pi r square. So that is the enclosed area. Now since the sphere is carrying a uniform surface charge density, so what will be the charge on this area? So therefore the enclosed charge Q enclosed will be pi r square into sigma. Pi r square into sigma. So once you know the Q enclosed, then what will be the flux through this Gaussian surface? Q enclosed divided by epsilon naught. So in this case it will be pi r square sigma divided by epsilon naught, divided by epsilon naught. So that will be the flux through this Gaussian surface. So there is some mistake in option, so you can just divide each option by epsilon naught. So then which options will be correct? Pi sigma r square divided by epsilon naught. Option A will be correct. Okay, option A will be correct. So I hope you get this point. So we have a two sphere, but they are not concentric. The center is shifted by a distance r. So because of that, the Gaussian surface will enclose a portion which will be look like this, a spherical cap. It is not a hemispherical surface, it will be less than the hemispherical surface, so it will be like a spherical cap. So first we have to calculate the area of this cap portion. How we can calculate? We can just write the elemental area on the spherical surface, and then for a complete spherical surface we take limit theta 0 to pi, but for this type of spherical cap portion, in this case we have calculated that this angle will be theta will be 60 degree. So in this case, if we take the limit of this integration 0 to pi by 3, that will give us only area of this portion. Now the charge per unit area is sigma, so the charge on this area will be this area into charge, and since it is a Gaussian surface, is closed surface in this case, so flux will be Q enclosed divided by epsilon naught. So correct option will be option A. Okay, and yeah, so this is another question. So what is written in this question? That electric field is equals to alpha r square r cap exists in space. The total electric flux through the sphere of radius r center at origin. So in this case, we have an electric field, but you see here, if we put the different value of r, then electric field will be different. And also we know in spherical polar coordinate system, r cap is a function of theta phi, so it's a non-uniform electric field. So given electric field is non-uniform, and then what has been asked here, if we consider a sphere of radius r, center at origin, then what will be the flux through this sphere? So let me draw a quick figure. Let's say this is x-axis, y-axis, z-axis, and this is a sphere of radius r whose center is at the origin, center of the origin, and in this region we have this electric field E is equals to alpha r cube r cap. Alpha r cube r cap. Then what we have to do, we have to calculate what will be the total flux. What will be the total flux through this surface. So particular in this case, when we have an electric field and it is given in spherical polar coordinate system, and also the surface through which we have to calculate the flux, it is also given in spherical polar coordinate system. So in this case, if examiner asks you to calculate total flux, so we can calculate this flux actually using surface integral. Flux phi is equals to E dot ds over this closed surface. Okay. For that, what we have to do, first we have to consider elementary area on the surface. So it's a spherical surface. What will be the elementary area? The radius of the spherical surface is capital R, so r square sine theta d theta d phi. This will be the elementary area. And also we have to calculate the value of electric field at this point. So what will be the electric field at this point? The surface. So first we have to write the value of electric field on the surface at this point. So what is the distance of this point from the center? It will be capital R. So we can replace this small r by capital R. So it will be alpha capital R cube into r cap. So that is the value of electric field on the surface. And then we have to take the dot product with the elementary area. So in this case, elementary direction of elementary area will be along r cap, spherical polar coordinate system. So you have to take dot product with r square sine theta d theta d phi r cap. So now r cap will give you 1. And then limit of theta, since it's a complete spherical surface, so it will be 0 to pi, and for limit of phi will be 0 to 2 pi. So after taking the dot product, what you'll get alpha and r to the power 5. These are constant, you can keep it outside. And then what we have to do, we have to take the integration of sine theta with respect to theta over the limit 0 to pi. And also we have to take the integration of phi d phi over the limit 0 to 2 pi. 0 to 2 pi. So then what will be the value of this integration? This integration will give you 2, and this integration will give you 2 pi. So ultimately we'll get 4 pi, and then alpha and r to the power 5. Alpha and r to the power 5. So correct answer will be option B. So total flux will be 4 pi alpha r to the power 5. Okay. So if we have a non-uniform electric field and have a closed surface, and in this case, let's say if electric field is given in spherical polar coordinate system, and the surface through which we have to calculate the flux, if it is also given in spherical polar coordinate system, then we can calculate this flux easily if we use this surface integral E dot ds. But sometimes what examiner give electric field in terms of rectangular coordinate system, and then give a spherical surface and ask to what will be the total flux through a spherical surface. Well, electric field is given in rectangular surface, but the surface instead of spherical surface, examiner can give you a surface which is cubic surface. So on the cubic surface, if you want to calculate this flux, cubic surface is also closed surface, cubic surface like this. This type is also closed surface. But in this case, if you want to do the surface integral, then how many integration you have to do? For 6 surface you have to do 6 integration, and it will take quite long time. So for this type of situations, what we'll do, we can just take the divergence of this electric field, that will give us the volume charge density associated with this electric field. We multiply with epsilon naught as we have calculated here. Calculated here, not here, Gauss law, here. So if we take the divergence of electric field and then if we multiply with epsilon naught, that will give us the volume charge density associated with this electric field. So once you know the volume charge density, and then you can just take a volume integral over the volume that will be given in the question. So when you do the volume integral, when there will be a, if the electric field is given in rectangular coordinate system, but surface through which we have to calculate the flux, if it is given in spherical polar coordinate system, then you can, instead of this surface integral, you can just take divergence of this electric field, and then you calculate the charge density associated with the electric field, and from there you can calculate what will be the enclosed charge, and then if you divide it by epsilon naught, that will give you the flux, total flux. Or when you will use this, when either charge density is given, let's say in terms of xyz, but the surface is given, it's a spherical surface, or let's say electric field is given in terms of xyz, but the flux through which the surface through which we have to calculate the flux, it's a spherical surface, or let's say cubic surface, or let's say cylindrical surface. Cylindrical surface. So for this type of situations, I will always request you, don't use this surface integral. Don't use this surface integral. There is a chance that you will get a wrong result, because for surface integral you have to do a lot of things for this type of situation. So for this type of situations, what will be the better way? First you write the divergence, take the divergence of this electric field. From there you will get volume charge density. Volume charge density inside the sphere, inside the cube, or inside the cylinder. And then you just take this volume integral of this flow over this sphere, or over this cube, or over this cylinder. You will get the enclosed charge, and once you know the enclosed charge, if you divide it by epsilon naught, that will give the flux. Okay, so I hope you get some idea how to calculate flux for different cases. So this Sunday, today is Sunday, so this week I'm not going to upload any test. So instead of test, what we'll do, maybe today or tomorrow, by the tomorrow evening, I will first complete another lecture based where we'll calculate electric field because of symmetric charge distribution using Gauss law, and then I will upload a practice set where you will get a similar type of questions that we have already solved here. So you first complete this practice set, and then next week we'll upload a test. Okay, then thank you for watching. See you in the next video. Bye bye.